Yeah, thank you very much, Yongjun, for the invitation here. It's my first time at this university in KAIST. It's also my first time in South Korea. So I'm very excited and I like it a lot. So I will now talk about chemotaxis, which is an area I have worked on a lot in the past. But in this talk I will focus on what I call anisotropic diffusion. And the talk has basically two components. One is mathematics and the other is applications. And the applications, you will be surprised, vary over quite some different areas. So you see on the very top, so here on the very top, item 3 would be Wolf movement. So one little application is about Wolf movement. Another application here, number 5, is glioma, which is brain tumors. And actually, brain tumors is really the main motivation for me to study all this, because we want to make some progress in the treatment and the understanding of how brain tumors progress. Here are two of my collaborators. Amanda Swan is a PhD student. She's finishing this summer. And Kevin Painter is from Harvard University in Edinburgh. And he and we have worked on a lot of this stuff together. Okay. So here's a little bit the outline. First I will talk what I mean about fully anisotropic diffusion, motivated from cell movement in fiber networks. And then I talk about the wolf and the glioma. And then here in the middle, item 4, I show you an interesting blow-up result, which is kind of unexpected, but it comes out of the anisotropy of the diffusion. So what do I mean with fully anisotropic? Fully anisotropic diffusion, I mean this equation here. So it looks like a parabolic heat equation basically, but you have a diffusion matrix or diffusion tensor. So D is a matrix, and then here we have the entries Dij, and then we take the full second derivative of this object Dij times U, and I use summation convention. I'm sure most of you are familiar with this. So it's a summation over I and j. In short notice, I write it like this with two nablas. So this is not Laplacian. This is really the full second derivative. Some people use a colon in here. So it's, yeah, so I'm not doing this, but it could be used to show that this is kind of a trace of an operator. Okay. I will compare it a lot with what I call now Fickian anisotropic diffusion. So a different way to write anisotropic diffusion would be this. So here D could also be a diffusion tensor. But then you apply one derivative directly to U and then the other derivative outside. And the question is, which of these two models is, I don't know, better, or which is more useful, or which shall I use if I talk about wolf and glioma, for example. So the first little bit of my talk, I will contrast these two ideas and show you a little bit where they come from and what advantages or disadvantages could be. So, fully anisotropic diffusion, where does it come from? Where does this model come from? What are mathematical properties and what can it be used for? That's basically the purpose of my talk here. So let's look at the one-dimensional case. So in 1D, I just assume I have a diffusion coefficient, but now this is spatially dependent. It is no longer constant. And again, I can look at these two models. The one is called Fickian diffusion, where the d of x is between the derivatives, and then the Fokker-Planck kind of idea where the d of x is inside the two derivatives. And of course, I mean, you can apply one derivative and then you get one of these terms and then an additional advection term. So the question is, what does this additional advection term do? Okay. So let's look at steady states first. So I just set this term to be equal to 0. And then for Fickian diffusion, if you have, let's say, no flux boundary conditions, then you get constant steady states, and that's it. Nothing else. For the other case, for the Fokker-Planck case, again, you look at steady states, and you find that steady states are proportional to 1 over d of x. So where there is high diffusion, there's not many species, and where there is low diffusion, that's where the species accumulate. So this system here allows for non-constant steady states. And in many biological applications, this is very important to have non-constant steady states. Okay. You can derive this from the perspective of random walk. I know many of you are quite familiar with random walks. So we have a line and we have particles jumping on a grid. And ui of t is a probability to find a particle at xi at time t. And then the transitional probabilities are Ti plus minus. So these are the probabilities to jump right or left. And then we can write down the evolution in a master equation where we have jump to the right from I minus 1, or jump to the left from I plus 1, or you jump away from I either to the right or to the left. And now it depends on the choice of these transitional probabilities what kind of model you have. In particular, we would like to make the discretization small and small and small so that we get a continuum equation. And then it depends on the scaling of those t's what you get out of this. And I'll show you now 3 cases on the next slide. So the first case I call look locally. So this means the transitional probability at location I depends on xi. So it depends on the information where you are sitting. So you're standing in a certain location, and then you decide, do I move somewhere or not, based on my current location. Now this delta x to the minus 2 is the appropriate scaling. That's not so important. But this dependence is important. And then in the limit, you get out this diffusion equation where the t of x is inside of the 2 derivatives. If you look ahead, that would be the next case. So now the transitional probabilities depends on the point you would like to move to. So now I stand here and I look there. And if it's better in my neighbor's garden, then I go to my neighbor. And so then this leads actually to kind of a funny term, which has a diffusion term and a drift term here. And then look ahead halfway. So now the transitional probabilities depend on the information between the grid points. Then you get one derivative inside and one derivative outside. So from this point of view, from this random walk derivation, you can, so this here has been studied to death. This has been studied a lot. We know everything about it, but this has not been studied as nearly as complete. But from this kind of derivation, there's no reason why you should not study this and focus all your energy on this one. So I think each of these models has a very good justification and can be looked at. So a summary of these is given in Othmar Stevens or Okubo Levin. This is a textbook where this is laid out quite nicely. Another idea is the ideal free distribution. The question is, where do you find species? If you have biological species in the landscape, do you find them homogeneously, or are there hotspots where you find them and other spots where you don't? So for example, when we go out in Canada for a picnic outside, then you can be sure that all the mosquitoes are exactly there where we have the picnic, and probably no mosquitoes are anywhere else. So Fredwell and Lucas framed this ideal free distribution. Actually, this has nothing to do with thermodynamics. So it is not a free distribution in the sense of thermodynamics. Species distribute themselves such that the fitness of each individual is the same. Mathematically, this means if you have a resource landscape, m of x, so this is how the resource is distributed, then the ideal free distribution is expressed if the population density is proportional to m. So where there's lots of food, you find a lot of species. Where there's no food, you find no species. Yongjung Kim, with many of his students, has written a series of papers of what he calls starvation-driven diffusion. And this is a model of this type. And this model obeys the ideal free distribution. So steady states obey the ideal free distribution. And he also showed that in some situations, this ideal free distribution is a global attractor, where everything converges to. Important here, again, the 2 derivatives outside of the diffusion term. That's the point I wanted to make. So again, it has kind of this Fokker-Planck kind of idea in it. Also recently, this is a paper by a student of Philip Maini from Oxford, and he called it the myopic model, which can explain bacterial population patterns at interfaces where the Fickian model cannot. So there are some reasons why this, what I later call fully anisotropic model, is actually a useful model. So let's look at cell movement in fiber networks. So let's get closer to the brain tumors. But first I start with melanoma of the skin. So this is a schematic of a skin cancer cell. And then the skin is made up of all these collagen fibers, which are indicated here in these black lines. And these melanoma cells, they crawl through the skin and they follow the guidance of the fibers roughly, but they also cut. So here where the cell came from, it has cut through the fibers which are in the way, they are degraded. so that they can pass through. So what I like to do now is to develop a mathematical model for this process. So I have moving cells. The cells change direction depending on the fiber structure. At the same time, they modify the fibers by cutting through them. So before I do this, I'll show you two little movies, so where you can see how these cells move. Of course, it is not as clear as I've shown it in the sketch. But so here's a cell, and this is part of the same cell. It's just out of the plane of focus. The gray background is the collagen fibers. And then in the central slides, you see a little bit better that there's some cutting where it came from. There's some fibers missing. And so it's pulling on the network, but it's also cutting through the network.
So if it's cutting the network, then it's not reversible.
And that is non-reversible, right. So then there is like a tunnel, and then other cells can use the tunnel and follow and invade as well. And this we can see on the next movie. So here, this is super short, so I show it twice. So that's it. So what you see it. The screen split in two parts, and you have a tumor sitting here and a tumor sitting here, and then you see individual cells coming out of the tumor, and they're doing exactly this. They cut through the network, and they form like a tunnel defect, and then other cells can follow and invade. And so that is the first step of forming metastases. So let's look at this again. So I stop it here. And so here you can see individual leading cells, or here, and then but also you can see kind of the roads they are building to go through there. Okay. All right. So let's come to the mathematical model. It will be a kinetic equation, because I have to talk about directions. I have directions of the fibers, and I have directions of the cells, and I want to compare how do the cells move along the fibers. So to denote the fiber orientation, I use theta, which is the unit vector. And I have two types of fibers, undirected or directed fibers, and collagen is undirected, meaning if I sit on the fiber, I cannot say what is up or down, or plus or minus, or positive or negative, or something. It is equivalent. Whereas directed fibers, such as microtubules or actin filaments, you know exactly where is up and where is down. Okay? So I'm in this situation for the cancer situation here. And then I look at a distribution of the fibers. I call this QTX theta. So at each time, at each location, I have fibers, fiber directions. And this Q is a distribution of all these directions which are present. And so integrating over all directions, this normalizes to 1. Okay. Then I talk about the cells, and the cells have a possible velocity. I mean, you saw in this experiment, you can easily measure the cell velocities. And the only thing I need is that this is a compact set. So maybe you have a minimum and a maximum velocity, and then you can have any direction. And v hat is the corresponding unit vector. And then a technical detail, I need to lift the distribution Q and make it into distribution over V. And V is the larger space. And I can do this by using a normalization constant omega. And then omega can be computed. So the formula is not important. It is only important that omega is a scaling parameter which shows up all the time. And that's what it does. Okay. So then here's a transport equation for this, and actually this motion is called mesenchymal motion, because these are mesenchymal cells. So let's go slowly through this equation here. We have P is the cell density, and Q is the fiber density, or the fiber orientation. So then this first equation describes the movement of the cells, and the second equation describes the cutting, how the cells cut the fibers. Now for the movement of the cells, they move in a direction V. So this is just the characteristic derivative. And then the right-hand side describes how they change direction. And mu is the turning rate. So they change direction. So this term minus mu p, they change out of the direction V. And then they choose a new direction by this term. But this term is proportional to Q. So this says that the new direction is chosen from the fibers. So if all the fibers go this way, then the cell will also go this way. And if the fibers are completely random, then the cell chooses any direction. So the idea is that the new direction is chosen from the underlying fibers, which is Q, And then the omega is still there, as I told you. Okay. Now the cutting equation is more complicated because it involves these projections down here. So just in a nutshell, the idea is if a cell encounters a fiber which is perpendicular, then it will cut it with a high probability. If it's parallel, then it will just slide along and will not cut it. And so what you need is a projection which is here. So the fiber direction and the cell direction. If this term is 0, so if they're perpendicular, then this pi is about 0, okay? So pi is 0, and you have maximum cutting. You have a minus term. If these terms are parallel, then pi is about 1, and you have no cutting. So this is basically how the model works. Okay. So now we take this system here, put it in the computer, and see what it does. And of course, what we like to see is this kind of stream-like invasion of cancer cells, etc. So the simulation is done by Kevin Painter. You will see, first you will see just green, which means uniform distribution of cells and uniform distribution of fibers, but randomly. And then eventually structures will form on that. So this movie is a bit longer. We have a bit more time to look at it. So you see, immediately you get some structures forming, and they form kind of highways. And these highways, they're getting sharper and sharper. They kind of emphasize. And then all cells, high density 4 to 5, is on these highways, and almost nothing is between these highways. So the system seems to, let me show this again because it's so cool. So the system seems to do exactly what we want it to do. So we have the cutting, but we also have the reinforce using the roads which are already present. Yeah, so that's really cool.
The blue regions are filled with the fibroblasts.
Yeah.
The blue regions is basically empty of cells.
And filled with fibers.
But there's still fibers, exactly, yeah. Yeah. So the fiber density is actually unchanged here. Okay. So now we have this kinetic model, the transport equation, which is here in the schematic on top. But I would like to scale it down to a diffusion equation, to a diffusion model, because diffusion models are easier to handle. And then this is actually what we need for the glioma study. So I would like to go here, parabolic limit diffusion equation. And then there are many ways to do the scaling, and here I show the three most prominent ones. So the moment closure, hyperbolic scaling, parabolic scaling. So the parabolic scaling goes directly down here. The hyperbolic scaling has a hyperbolic limit, which then, if it's diffusion dominated, can be scaled to become parabolic. Or the moment closure takes a detour over balance equations and then goes down here as well. So there's a lot going on in the slide. This is way too much to explain. In fact, this is the content of the summer school, which you are organizing in 2 weeks. So if there are students here interested to learn more about this, I will go through all the details in a series of lectures in that summer school. But here I show you a little bit. For example, for the hyperbolic scaling. So then we scale space and time by a small parameter epsilon. And so then the epsilon arises here. This is the right-hand side of the transport equation. And then we use something which is called the Chapman-Enskog expansion. Look at leading order terms, etc., etc., and I'll show you the leading order term. So the leading order equation is this, which is a pure hyperbolic drift equation, and the drift velocity uc is given by this integral v q over omega dv. Now q over omega is a probability distribution on v, on the capital V here. So then this here together is the expectation. Okay, so the drift velocity is given by the expectation of the fibers. So as I say, if all the fibers go this way, then the expected direction of the cells is the same direction. So UC is the mean value of Q divided by omega over V. But then for undirected tissue, like for the collagen fibers in the skin, this is actually 0, because it's symmetric. So then for the parabolic scaling, we scale the time with an epsilon square and the space with epsilon. So they have different orders in epsilon. So you get an epsilon square here. You do an expansion in epsilon, and then the leading order term is actually a diffusion term. But this is a fully anisotropic version. It is nabla dp, where d is a tensor, it is V transpose Q over omega. Or you can write it V tensor V. So there are different ways to write this. So this is the diffusion matrix or diffusion tensor entering here. And this is a fully anisotropic diffusion equation you get out. Now this also has a meaning. Since Q over omega is a probability distribution, then this is the second moment, or the variance covariance matrix. So D is a variance covariance matrix of Q over omega. Okay. So if you do the moment closure and assume fast moment relaxation, you get both terms at the same time, this drift term and this diffusion term. So then the procedure is you need to find Q. So whatever your biological situation is, we need to find what Q is, the Fibre distribution. Then we can compute these moments, U, C, and D, first moment, second moment. We can plug it into the drift diffusion model, and then we have a diffusion model for our problem. Okay. So the question is how to find the directional distribution Q in a given situation. And the answer is we use a von Mises distribution. And to introduce a von Mises distribution, it is now good to talk about Wolf. So let's detour to the Wolf and then come back to the cancer cells later. So Wolf movement. So now this is a typical Alberta problem. So here we have a landscape from Alberta. Well, this is not summer. This is spring, but there's still a lot of snow still on the ground. And so here you see roads. And this is a piece of forest, but also we have a very fine lines going through the forest. And these lines, they're more than you can actually see. These are called seismic lines. And so the oil companies, they cut through the forest and they set explosions in the ground and they want to measure where the oil is. They want to find oil. Okay, so they crisscross through the forest with all these lines. But then the wolf and the deer living there, they can use these lines now to invade. In particular, the wolf, they use the lines, they go further than they would normally go, and they're more successful in hunting, and then the deer population goes down. So it is a severe interaction with the ecology here. Mackenzie and Lewis, they have collected data and analyzed data about how wolves move in this environment with using collars, GPS collars on the wolf. Okay. So here we digitize the previous image. So these are all the lines on the previous image. So as I say, many more than you expected. And now we assume, right, and now it has been measured that if a wolf is on the line, then there's a higher probability for it to stay on the line, but still it can detour off and go back into the forest as well. And this can be described by a von Mises distribution. And here I show you the bimodal von Mises distribution. So it is a distribution on the unit circle, so over directions. And in this case, you have a dominant direction in this way and a dominant direction in the other way, where there's a maximum. Then it's kind of a normal distribution, or actually these are two normal distributions, which are wrapped around the circle. So the von Mises distribution is a circular normal distribution. And now this is a formula. So I0 is a Bessel function of order 0, modified Bessel function of order 0. And then it has these exponential dependencies where gamma is a given direction. So gamma would be this direction. And this k of x is the concentration parameter. So this tells you how wide the distribution is. If k is very large, then the distribution is very sharp. If k is 0, then this thing is just uniform. Okay. So, but then we have a Q, right? So now we have a Q. So then I can do what I told you earlier. I can compute the drift velocity, I can compute the diffusion tensor, and have a diffusion model. So let's do that. So then the drift velocity is actually 0. It has to be because the distribution was symmetric. But the diffusion coefficient is this tensor, again involving Bessel functions. But the interesting part is we have an isotropic part, this is the identity matrix, and we have a directed part, which is the dyadic product of gamma and gamma transposed, with a certain scaling in front of them. So then we need to solve this fully anisotropic diffusion equation for the Wolf problem. Okay. So often assumed in the literature is a setup of this form, kappa 1 identity plus kappa d gamma gamma transposed. And nobody knew what kappa 1 and kappa d is. And so using our method, we have a very clear identification of these parameters, which are used here. Okay, let's come to the simulation. So here we have underlying the lines and then a homogeneous distribution of the Wolf density. And then after a while, short time t is 10, we find that most of the wolves are along these lines. But also between the lines, the density is not 0, it is close to 1. So we find wolf also in the forest. And so this mimics the natural situation very, very closely. That's really nice. So then one step further, we can look at how far wolf spread out to hunt. So if they have a den site where they usually live, and so then in this network, they seem to spread out much more along the lines than they maybe would normally do. And so this can explain why they are more successful hunters in this situation. Okay, so then before I come to the brain tumors, let's talk about the blow-up result. And I also want to check the time. So I used about half an hour. I'm fast as always, okay. But nobody will complain. So this blow-up result is actually really cool, really interesting. It has to do with the wolf problem. So first of all, let's look at the fully anisotropic model again. So you can multiply it out, and then you get a diffusion term and a drift term here. No, what? This is the advection term. This is the diffusion term. It is still uniformly parabolic if D is positive definite, but it does not satisfy maximum principle. So even if you start with homogeneous solutions, you could maybe develop non-constant steady states, for example. And so now let's look at one road. So here's one road, one of these seismic lines, which goes this direction. And here's forest, and here's forest. And now I look at the extreme case that on the line, I have only diffusion along the line, and I have no diffusion up or down. So if I have a diffusion matrix D1, D2 in the diagonals, then here I assume D1 is 1 and D2 is 0. And in these forests, I have diffusion in any direction, so I have D is 1/2. So what happens? What happens if I have some initial condition and let it run? So it's what do you expect? What happens?
Everything the line on the road.
Everything should be on the road. That's right. Yeah, and something like this happens. Oh, here's the equation first. So D is a diagonal matrix. D1 is this term. D2 is this term. And then upper and lower part. So let's look at simulations first. What we get is this. So we start with a density homogeneous equal to 1. And then after some time, in fact, it accumulates along the line, but only on the boundary. Because on the line itself, there's no transport in y direction. So they just accumulate on the line, on the side. And this here goes to 0. And so then you get two peaks sitting right on the boundary. If you start maybe with initial conditions which are a bit more interesting, then again you get maybe a lower peak and a higher peak, depending on the initial conditions on the upper and lower part of this. Yeah, and this is what we have shown with Michael Winkler in 2012, that in fact the population density converges to two delta distributions sitting right on the boundary, and then whatever is on the line is kind of uniformly distributed along the line. So that's kind of neat. So although the original model, let me just go back, this one here, this is a linear equation, right? It's a linear equation. It sounds like boring like nothing else. But it still is able to show some very interesting phenomena. Okay. So let's come to the last point, which is the glioma. So I have a quiz for you. So where is this picture? Who knows where is this picture?
In the world there.
Yeah.
In the E2?
In E2, exactly, in E2, yeah, just between the, second and third floor in the hallway. Okay. So that's what I'm going to do now as well. I use brain imaging to study this. Okay, so here's some background on glioma. So here are two images. This is a typical MRI scan, and this is what doctors would see if they identify a brain tumor. It's a very serious thing, of course. So they have a tumor mass and then you have some edema around it, which is basically fluid. But then also you have tumor cells outside of this visible region, and it's completely unknown where these tumor cells are hidden. You cannot see them with this method, but you know they are there, and you want to treat these areas as well. And this is a schematic of the same thing. So what doctors do now is they take whatever is visible here, and they take 2 centimeters around, and then treat 2 centimeters wider than they could see. However, the brain has a very interesting geometric structure. And so we would like to use the geometry of the brain to maybe predict where the tumor cells have moved and not treat the area where the tumor cells have not moved so much. And this is called the brain anisotropy. And here is an anisotropy map of the brain. And this basically shows the major connections of the brain through nerve fibers. So one thing you can, so I think here's the eye. And so then there's one fiber which goes all the way to the back, to the visual cortex. So this would be the nerve fibers connecting the eye to the visual cortex, for example. And then there are other connections in this picture too. So now the idea is if a tumor maybe develops here, it would actually move more along the fibers and would not spread in other directions so much. So here are the nerve fiber tracks. These are shown from the side and shown from the top. And so it is known that tumor cells are guided by these, and they move along these fibers. So very similar to what I talked about, the melanoma, where they move along collagen fibers. So here now they move along nerve fibers. Okay? So again, here are some of these nerve fibers. And then using tractography, you can even visualize some of these nerve fibers in the brain, and then you get these fancy spaghetti images in different colors. So for that. Okay. And then here there are detailed studies how glioma cells follow these white matter fibers. So this is a cell, and you can see how it kind of follows the structures. Okay. So the information we use, we need some information about the brain geometry. And one interesting way to measure it is called diffusion tensor imaging. So this is DTI imaging. So here's a brain, and then this is overlaid with all these ellipsoids. And these ellipsoids tell you at each location how anisotropic this tissue is. So if cells move more in diagonal direction or in the other directions. And if you have a very cigar-shaped ellipse, it's very anisotropic. And if you have like a soccer ball, a very round ellipse, it is isotropic. Okay, so at each point you have these ellipses. Okay. So now the question is, we have this DTI information, all these ellipses, and we want to make a model for the brain tumors. So how to do that? How to use this information for the brain tumors? And the idea is we follow what I have developed already. So we need this intermediary Q. We need this directional field for the fiber network, and then let our cells move. Well, if we have Q, then we can compute the variance-covariance matrix, and then we have our macroscopic model. So stepwise, we obtain the measured DTI data. We define Q as von Mises distribution. So we use the same idea as for the wolf. The von Mises distribution does really well. We compute the tumor diffusion tensor as the variance-covariance matrix of this Q. And then we solve the anisotropic diffusion equation, where we add a logistic term because the tumor is growing. So we add a logistic growth term to it. Okay, so here is again Amanda, my PhD student, where she does a simulation on a 2D domain. So we started in 2D, of course. So you just see blue and an initial tumor here, but underlying is all the diffusion tensor imaging information. So this is a full data set of diffusion tensor imaging. And now I let it start. And then we see how anisotropic the tumor will grow. So you see lots of structure. So it doesn't just grow like a ball, which is round. You see lots of structure. You see high densities here and here and here. And you see some kind of fingering, irregular spread coming out of this. And this is exactly what we are after. So we would like to better understand this irregular spread coming out of the tumor. So then let me summarize. There was a lot going on here. So it was about fully anisotropic diffusion. Where does it come from? I talked about random walks, about the ideal free distribution. and then about transport equations and birth-jump processes. So they arise very naturally. There's no effort to get these models. Mathematical properties, they have pattern formation, non-constant steady states, and blow-up. And then what it's used for, glioma growth, wolf movement. And then also in a new study, we use it for sea turtle orientation. And this will be a talk which I give next week at NIMS, where then I use basically the same method, but for sea turtles, and how they find their island to breed. Okay, and more. So I think, this is the end of my talk. So thank you very much for your attention.